Now that you've had some experience playing with control systems, it's time to go back to this ARM simulation and see if we can approach it in a different way than perhaps what you used the first time. So this is the code that you start with in the basic simulation. We're going to comment out the ARM torque line because we want to tell this motorized arm what to do. You'll see I'm going to type a line set point. I'm going to define a variable set point, and let's say the angle that we want this to fire at is 30 degrees. And so the goal is to put in a torque so that the arm rotates around 230 degrees. Let's give that a shot using a simple on-off control system. This is code for a simple on-off control system, and I've defined some constants. Motor torque I'm just putting up here as 1,000, and that's so that it's easier to change that number outside of the code later on if that number doesn't tend to work. This is simply saying if the arm angle is less than the set point, then we're going to set the arm torque equal to the value of that constant. Otherwise, we'll set it equal to 0. Let's see how it goes. We can see that it doesn't do too badly as it's right at the 30 degrees. It's bouncing back and forth. So it's not great, but maybe that's good enough for the application. It's not good enough for me, so I'd like to see if I could do it maybe a little bit better down the line, but at least I have it controlling the angle in a way that it stays at 30 degrees. Let's now see what happens if I increase that angle to 45 degrees. And because I've defined the constant up here, I only have to change this in one place to test it. So something strange is going on. You can see that it is stabilizing at an angle that's below 45 degrees. It's greater than 30, less than 45. And so this tells me I maybe am not giving it enough torque. So maybe I need to give it 1,500. So my theory was right. It now has enough torque to kind of bounce around the 45. Maybe that's too much torque, so I can pull it back and make it 1,200 instead. Let's run it. Okay, so that number is maybe a little bit better, but it's still, that bouncing really bothers me. There's another thing that I'm going to do. Now that I have it working at 45, let's bring it back to 30 degrees and see what happens when I use this higher torque at the lower angle. You see, I get almost, I don't know that it's more bouncing or less, but it's still a little bit of bouncing. So this leads me to say that the on-off control system may not be the way I want to approach this. I could try on-off control with tolerance. And so I'm just experimenting on this. I'm saying that if the arm angle is below the set point minus tolerance, then I'm going to apply motor torque. If it's greater than set point plus tolerance, I need to bring it back down, and I'm just setting that equal to 80% of the motor torque that I put in there, just because I don't want to force it down, and I know that if I apply 0 torque, the arm just falls. So adding a little bit of torque that is less than that set point might be helpful. I do, of course, need to add that tolerance constant in here, and let's just say that the angle is 5 degrees. Let's try it out. All right, so it's working okay for 30 degrees. It's a little bit high, maybe. Let's push it up to 45 and see how it does at that angle. I still have a lot of bouncing around the 45, even with that tolerance. So this leads me to believe what I started to suspect before, and that is I need to use a different control system. And proportional is probably the way to go, so that's going to be my next step. To use a proportional system, we need to set up a few variables that we're going to use for our system. The first step is to set up a variable called error, which calculates the difference between where the arm currently is and where we want it to be. So in this case, that's going to be the set point minus the arm angle. The next step is to figure out the output torque that we're going to be applying to the arm. We calculate that by taking the error and multiplying it by a constant, k, that represents how strong we want the motor output, the arm output torque, to be controlled or connected to that error. Now we don't know what we want to use for this value of k, so I'm just going to guess and say that maybe it's around 100. So let's see how that goes. We're now going to apply the arm torque to be equal to that output. Let's see how we do. All right, now you can see that it definitely stabilizes at a certain level. It's not quite at 45 degrees, so our k value isn't enough to overcome the torque that is being exerted by the weight of the arm. So let's increase that k a little more, and a little more, and maybe a little more. All right, so this k value of 600 seems to be pretty good in terms of getting the arm up to where it needs to be. Let's use the same trick as we did before and decrease that set point to 30 degrees and to see if the control algorithm can keep up. So it looks like as this goes, it's continuing to bounce back and forth, so it's oscillating about 30. So this k value doesn't quite do it. Let's try a higher set point, maybe of 90 degrees. Now for a set point of 90 degrees, you can see it's almost there. Now when you are using a k value and your system doesn't quite reach the value that you're looking for, this is where an integral term can be useful. The way an integral term works is we're going to calculate the error, and we're going to also calculate a cumulative sum of that error over time. The idea being that if that error continues to be high, then what we'll want to do is, as the sum of that error gets bigger and bigger and bigger, we're going to increase our output in a way that is proportional to that cumulative error and nudge our system back a little bit more toward where we want it. Now, I've already defined a variable called SumError up here, so it's going to be available to my loop over and over and over again as it runs. What I do need to do is I need to update the sum of error every time the error is calculated. And now I'm going to add that sum of error as part of my output. And again, I don't know what number to use for ki, so I'm just going to guess that it's equal to 10. Let's see what happens now. So you see very nicely, even though the torque is higher than it needs to be, this cumulative error is settling my system back to where I want it to be, right at 90 degrees. Let's bring it back down to 45. And the system again works. And now let's try it back at the 30 degrees. Because that's what was giving our system trouble before. So now our system will be steady at 30, 45, 60, and 90 degrees. And we haven't tried any angles above 90 degrees. Let's see what happens when we give it one. Okay, and our system is able to adjust until it gets closer and closer to where we want it to be. So this is great. This is showing that our system is fairly flexible. It's going to the different levels that we want it to go to. But it still does a lot of bouncing. And that bouncing is a problem. We don't want that bouncing to be happening. So this is where we can actually apply another term to our output, which is what we call a derivative term. The derivative term is usually one that opposes the current velocity of how our system is changing. And so we're going to use the change in the error as the way that we're going to apply an opposing output. So it's going to be kind of like friction that we're adding to our system. Let's set up the code for this. All right, I've done a couple of things here. I have added a calculation for the change in error. That is the current error minus the previous error. So that's how much that error is changing. And I've subtracted KD, which is just a constant, times the change in error. So again, if the error is changing quickly, I don't want to add as much push to my arm up because I want to resist any sudden movements one way or another. The other thing to know about this system is I have to constantly within the loop set the previous error equal to the current error so that it's updating with every loop. Let's see how this goes. Okay, so there's still quite a bit of bounce there. I'm going to lower our set point back down to 45 degrees because that's where we had a lot of bouncing, and let's see how well it works. Okay, still quite a bit of bouncing, so let's increase the KD. Let's double it to 20. Maybe a little bit more than that. I'm actually thinking I might, because of how I calculated the change in error, let me try adding it. Oh, that actually makes it much better. So I had this calculation, last error minus error. Thinking about that, I want to calculate so that if my error is decreasing, I want to have an increasing amount of torque or correction. So sometimes you have to change the signs of the KD or the calculation of the error in order to get it to work exactly the way you want. So that worked pretty well. So now let's increase it maybe to 80, see if we get it even better. Not bad. Look at that. That's pretty quick. Okay, so 45 is pretty good. Let's increase that back to 90 to see how it works. And you can see it overshoots, but the integral term brings it back down until it gets to 90 degrees, which is great. And so now that we see it's overshooting quite a bit and the bouncing is being reduced pretty quickly, we can now reduce this K a bit more so that it goes a bit more smoothly. And we could even increase the KI. Whoa. See how it spins out of control? Sometimes that can happen, so we don't want to do that. So maybe we'll continue decreasing the K until we get what we want. And so let's bring it back down to perhaps 60 degrees below the horizontal and see how it works. Really smooth. Look at that. All right. So you can see that this process of changing the K values, which is called tuning, is part of the process of getting your system to respond the way you want it. And we've used this idea to get this arm to go exactly where we want it, and that's the hardest part of a complex control system, is adjusting the system so that you get exactly the behavior that you want. So I hope I've helped you understand how we can turn this complex control problem that's hard to do manually into one that we can automate using some clever uses of proportional, integral, and derivative control algorithms. See you next time.